Hi, ladies and gentlemen. All right, so we've reviewed Newton's first law of motion, right? We've talked about what it takes for either an object at rest to move, as in question number one here, or what causes a moving object to stop moving, as in question number four here. In both cases, an unbalanced force would need to be applied in order to change the movement, either from rest to moving or moving to rest. We know that another name for Newton's first law is the law of inertia. We know that inertia is a word that is used to explain or describe the tendency of an object to want to continue in whatever kind of motion it's in. If it's at rest, it wants to stay at rest. If it is moving, it wants to stay moving at that same speed and in a straight line. And then we also know that the more mass an object has, the harder it is to change its movement. That's because it has more inertia. And the less mass an object has, the easier it is to change its movement, and that is because it has less inertia. All right, so now we're going to branch into Newton's second law. Make sure that you have the notes page for Newton's second law here as we get started. What does Newton's second law say? Well, the second law of motion says that the acceleration of an object depends on the mass of the object and the amount of force applied. This relates really closely to Newton's first law because it relates very closely to this idea of inertia. You can see here that we're talking about the mass of an object, and of course, inertia has everything to do with the mass of an object. The more mass an object has, the more inertia it has. The less mass an object has, the less inertia it has. And so the acceleration of an object is dependent upon the mass or the inertia of the object, not to mention the amount of force that is applied to that object. So let's take a look at what we mean by this. We're going to need some volunteers. So we're going to need one person to volunteer to be the pusher. Probably a kind of medium-sized person in the class. We're going to need one of the smaller people in the class to volunteer to be a rider. And then we're going to need one of the larger people in the class to also be a rider. And then we're going to need one of the desk chairs. All right. So I'm going to pause. Let's pause for just a moment while these three people are chosen. All right. Hopefully, you've had a chance to choose your pusher and your two riders, your smaller one and your larger one. And what I would like you to do is to go ahead and start by putting the small rider in the chair. So, small rider, have a seat in the chair. And pusher, you are going to try to push the chair, oh, I don't know, 4 or 5 feet. Um, you might need to kind of push down toward the lower part of the chair so you don't just tip them over, but you actually slide the chair across the floor. All right, let's pause the video while you do this. Okay, so the small rider should have gone for their ride at this point. Now let's change and have the larger rider have a seat in the chair and pusher. Once again, you are going to go ahead and try to uh, push the chair 4 or 5 feet across the floor. Go ahead and pause the video while you do that. Okay, so here's the question. Pusher, was it harder to push the smaller rider or the larger rider? Well, hopefully you found that it is easier to push the smaller rider. Okay, in order to accelerate the rider, accelerate the chair, it is that acceleration is dependent upon the mass of the object and the amount of force applied. So the mass of the second rider should have been greater than the mass of the first rider. Therefore, in order for the acceleration to happen, more force would need to be applied. All right, so let's take a look at this law. We're going to kind of break it into two parts here. And we're going to start by taking a look at how acceleration is dependent upon the mass of an object. So the first thing we're going to say here is that the acceleration of an object decreases as the mass increases. So the more mass there is, the less acceleration there is going to be. Right now, we're assuming that the force stays the same the whole time. Okay, so if you are accelerating an object across the room and all of a sudden the mass of that object gets larger for some reason, okay, you're pushing a chair with a person in it across the room, and all of a sudden that person is holding 30 bricks, okay? The acceleration is going to decrease. However, the acceleration of an object increases as the mass decreases. So if the mass of an object becomes less, then when that same force is applied, the acceleration is going to increase. It's going to get faster quicker. Take, for instance, these two grocery carts. We've got an empty grocery cart. We've got a very full and heavy grocery cart. Which one is going to be easier to start pushing? Okay. I think we can all agree that the empty cart, the one with less mass, is going to be easier to start pushing. And that is because uh, it has less mass, right? So therefore, it has less inertia. Doesn't want to change its, or it will change its its movement more easily than the one with more mass. Now, we could also make the point that because the full cart has a greater mass, once we do get that one accelerated, it will actually be easier to keep that one accelerated, harder to stop it, again, because of its inertia, because of its mass. But in order to get it started, the one with less mass is going to be easier to accelerate. So we looked at the fact that acceleration depends upon the mass of an object. And actually, if we go back to this slide for just one moment, again, you will notice that it says that the uh, acceleration decreases when the mass increases, and when the acceleration increases when the mass decreases. We call this an inverse relationship because as one thing is decreasing, the other is increasing, or vice versa. They don't both increase or both decrease. So we call this an inverse relationship between these two objects. We're going to see that's a little different when it comes to acceleration and force, because the acceleration of an object actually increases as the force on it increases. And really, it's pretty logical if you think it through, right? The more force you apply to an object, the greater its acceleration is. Okay? The acceleration of an object decreases as the force decreases. Okay, so this is not inverse. All right. This is a direct relationship, because as one thing increases, so does the other. As one thing decreases, so does the other. And so we can actually use math to explain Newton's second law and to calculate Newton's second law. And this is the formula. There are actually a couple of ways to kind of write this formula, but this is one way to do it because we've just talked about the fact that the acceleration is dependent upon the force of the object, or excuse me, the force that is applied and the mass of the object. So in this particular case, A stands for acceleration, F, of course, stands for force, and M for mass. The units that we use, okay, just as we did when we talked about speed and acceleration, acceleration units are meters per second squared. Force is newtons, capital N, all right, for newtons. And mass is the units that we use is kilograms. Okay, so let's take a little bit of a look at this. It gets a little tricky. We actually technically speaking, cannot do math with newtons. We actually have to change newtons to something else. And we can say that 1 newton is the exact same thing or equal to 1 kilogram times meter per second squared. What? Yep, that's right. 1 newton is equal to 1 kilogram times meter per second squared. Okay. So, well, actually, let's back up a little bit. Let's take a look at um, this idea here. Well, actually, let's just take a look. If 1 newton is equal to 1 kilogram times meter per second squared, then that means 4 newtons is going to be equal to 4 kilograms per times meters per second squared. It also means that 500 newtons is going to be equal to 500 kilograms times meters per second squared. 12 newtons is going to be equal to 12 kilograms times meters per second squared. I think you get the idea here. 395 newtons, of course, will be equal to, that's right, 395 kilograms times meters per second squared. So the reason we can say this is because force, let me see if I can get this to right here. Force, which we say is a newton, right, is equal to the mass, which is our unit is kilogram, and that is multiplied times the acceleration, which of course is meters per second squared. Sorry, I'm writing with my finger, so this is a little slow. All right, so 1 newton is equal to 1 kilogram times meter per second squared. All right, hopefully that makes sense to you. And let's see if I can get that to go away now. Oh, there we go. All right, so another way to take a look at this particular formula is to use the triangle, like we did when we talked about speed or acceleration or velocity. In this case, in our triangle, force is at the top, and then mass and acceleration, doesn't matter what order they go in, but we usually do mass first and then acceleration. Okay, so force is equal to ma, or m times a, mass times acceleration. Mass is equal to force divided by acceleration, and acceleration is equal to force divided by mass. So let's take a look at an example here. We've got an apple. It weighs 0.102 kilograms, so 102 thousandths of a kilogram. The force is 1 newton, so we're going to apply 1 newton of force to this apple. What is its acceleration? Well, we know that acceleration is, let's see if I can get my pen back up here. We know that acceleration is equal to um, force. Sorry, I know this is terrible. Don't have my pen with me, guys. Okay, force divided by mass. Okay, so the acceleration would be uh, a force of 1 newton, which technically is 1 kilogram. So 1 kilogram times meter per second squared. And then that's divided by a mass of 0.102. That's supposed to be a 2, just in case you're wondering. Kilograms. Okay. So if you grab your handy dandy little calculator and you do 1 divided by 0.102, you will get 9.8. And the reason it's meters per second squared, well, it's acceleration, but mathematically speaking, this kilogram and this kilogram cancel each other out because kilograms divided by kilograms takes out the kilograms, and then we're left with meters per second squared. So our answer is an acceleration of 9.8 meters per second squared. All right. So here's another practice question for us. What is the acceleration of a 3 kilogram mass if a force of 14.4 newtons is used to move the mass? So once again, we've got acceleration is equal to force divided by mass. And they are asking for acceleration, right? So that means that we've got a force of 14.4 newtons. Technically, to do the calculations, that means we have 14.4 kilograms times meters per second squared. Sorry about my writing. All right, and we're going to divide that by the mass of 3 kilograms. Again, kilograms are going to cancel out. 14.4 divided by 3. Well, if we bring up our calculator here for a second, and we figure out that 14.4 divided by 3, whoops, we'll bring up our calculator, 14.4 divided by 3. That, of course, equals 4.8. So we've got 4.8 meters per second squared is our acceleration. All right, so ladies and gents, let's take a look at this next one. What is the acceleration of a 7 kilogram mass if a force of 68.6 newtons is used to move it toward Earth? Same idea here. Again, we're looking for acceleration, so we're using the same formula. We're going to use acceleration is equal to force divided by mass. So in this case, our force is 68.6. We're going to divide that, and that's 68.6 kilograms times meters per second squared, also known as a Newton. And we're going to divide that by 7 kilograms. So the kilograms cancel out. We're left with meters per second squared, and we're given an answer there of 9.8. So 9.8 meters per second squared is our acceleration. Okay, let's take a look at another question. What force is necessary to accelerate a 1,250 kilogram car at a rate of 40 meters per second squared? Well, this time we're not asked what the acceleration is. We're asked what the force is. So, ladies and gents, if we're asked for force, then we are probably going to need the reminder here that we're not doing A equals F divided by M. Instead, we're doing force is equal to mass times acceleration. So if force is equal to mass times acceleration, F equals ma, FMA, all right, then let's go ahead. Whoop. If we do 1,250 kilograms, which is the mass, times the acceleration of 40, that is going to tell us how many newtons we need to have. And I can't get my calculator up here at the moment. And so instead, let me go back for a second. My apologies. All right. So hopefully you have, with your calculator, gone ahead and figured out that 1,250 kilograms times 40 meters per second squared is equal to 50,000 newtons. Okay, 50,000 newtons of force. All right, here's a challenge question for you, I suppose. Zookeepers carry a stretcher that holds a sleeping lion. Total mass of the lion in the stretcher is 175 kilograms. The lion's forward acceleration is 2 meters per second squared. What is the force necessary to produce this acceleration? All right. So remember, force equals ma. Let's pause the video and give you a couple minutes to calculate an answer. All right. So, ladies and gentlemen, again, force equals ma. Force equals mass times acceleration. Our mass is 175 kilograms. We're going to multiply that times our acceleration of 2 meters per second squared, which gives us an answer of 350. 350 what? Well, it's 350 kilograms times meters per second squared. Another way to say that is 350 newtons. All right, ladies and gentlemen, I hope that you have a great day. Make sure that these notes are put into the current unit section of your binders. All right, thank you.